This problem reads, a nuclear power reactor generates 3.0 times 10 to the 9 watts of power, which is 3 billion watts, or 3 billion joules per second. In 1 year, what is the change in the mass of the nuclear fuel due to the energy being taken from the reactor? Just a little bit on the units and comparison. So it says 3 billion watts, 3 billion joules per second. That would have to be multiplied with the number of seconds in a year. That's the 31 million seconds, and we would come up with how many joules it generates per year in the neighborhood of like 10 to the 17 joules. But I just want to show here in comparison that is actually a pretty big power plant. It says 3 gigawatts, 3 billion watts, and notice these are all 2, 1, 3, 1, 2, 3, and so on gigawatts. It says here 2000 megawatts, but that would be also the same as 2 gigawatts. So that really they chose a really big power plant. The way it compares to energy consumption, and actually I just looked up electricity consumption because that's what nuclear powerhouses are producing as electricity, and if I just look at the US, then I come up here with 4 million gigawatt hours per year is what's needed from any kind of fuels. And let me just show you how that compares. I need the calculator. So I'm going to use the 3 gigawatts from the powerhouse. By the way, what I'm doing right now actually is not necessarily for the problem. Sorry about that. Not to mention that earlier, but I just want to show that in comparison. So I'm going to use the 3 gigawatts and I multiply that by the number of days in a year, and I multiply it by the hours, and I leave it at hours, not multiply it by minutes and seconds. Then what I come up with here is now in watt hours, and that 2 times 10 to the 13 watt hours can be better compared to this one here because this also says watt hours. This one, yeah, so this one here is to 26 trillion watt hours. I guess that number means. Now I'm going to use this number here, the 4,400,000 gigawatt hours. So I'm going to type 4.4 10 to the 6 initially. This here says 4.4 million, but then there's another giga in front of it, which raises the power by another 9. So it's actually 6 plus 9, which is 15. And I divide that number by the 2.6 10 to the 13 watt hours that this power plant in the problem produces, and I come up with a number 167, and that number means that if there were 167 such power plants in the United States, that would produce the entire electricity needed for the United States. Or so 167 such power plants. Or you can look at it, well, how big of a city would you need? Well, we have somewhat around 330 million people living in the US. If we divide 330 million by 167 in order to come up with just one power plant, we come up with the size of a city of 2 million people that could be powered for the electricity with just that one power plant. Okay, again, all I did in the past few minutes here actually had nothing to do with the problem, but I just wanted to put that in relation. Pretty big powerhouse, and it could power a pretty big city, the example they give us here. But now I finally will do the problem. So it says that the power is given as, let's see, was it 3.0? Yep, 3.0 times 10 to the 9th watts. Okay, when I multiply that power with the time, and the time here would have to be in seconds, so that's the 3 point, how much was that? 3.16 times 10 to the 7 seconds. and this one here is 3.0 times 10 to the 9th, so roughly 1 times 10 to the 17 watt seconds, respectively, joules, and that would be the energy that it would generate per year. So energy per year, as I multiply with the seconds in a year. Where does that energy come from? Well, it comes from the mass deficit of fissioning, for example, the uranium, and that mass deficit is calculated as E equals delta M times C squared. And so this is the same as this here, respectively, since we're supposed to figure out what this one is. I set this one equal to that, and then divide by C squared. So we're going to come up with that delta M times C squared equals PT, respectively delta M equals power times time divided by C squared. And then I can plug this in on the calculator. And I would get, let's see, 3.0 10 to the 9th times 3.16 10 to the 7th. Pretty big numbers here. Divide by 3.00 10 to the 8th squared. And I come up with 1.05, or rounded 1.5 in standard units for the mass, which means it's going to be in kilograms. 1.1 kilograms is the mass deficit when uranium is used, for example. Now that doesn't mean I need just 1.1 kilogram of uranium, but it means that when they're done with the uranium that they're using throughout the year, that the fission products they get out of it have a combined mass that is 1.1 kilogram less than the original uranium that they had. And I didn't look that up. I'm guessing that they perhaps need 1,000 or 2,000 kilograms of uranium to fission every year in order to get that much power by just a mass deficit of 1.1 kilogram out of those 1 or 2 tons. I get those two numbers I just made up because I didn't research those. This problem reads: an intergalactic cruiser has 2 types of guns: a photon cannon that fires a beam of laser light, and an ion gun that shoots ions at a velocity of 0.950 times the speed of light relative to the cruiser. The cruiser closes in on an alien spacecraft at a velocity of 0.800 times the speed of light relative to the spacecraft. The captain fires both types of guns. At what velocity do the aliens see the laser light, the ions approaching them? At what velocity do the aliens see the laser light and the ions move away from the cruiser? Okay, and I just noticed that I need a second spacecraft. So here it is. Then I guess one goes after the other. There we go. There. All right. Okay, so 2 kinds of guns are being fired. One of them here moving with the speed of light, that would be the photons, and then the other one moving here with, what was that number? Shoots ions, 0.950 times the speed of light. Those are the ions. Because those are particles, they necessarily have to move slower than the speed of light. And then the ship itself is moving at a speed of 0.800 times the speed of light. And that would be relative to this one. This one is actually also moving, but this one here would be a relative speed between this spaceship and that spaceship. This is how much, so to say, faster it is. You know, the relativistic addition of velocity comes in here. But yeah, in relation, this is how much they measure how fast this one is. Okay, the first part is actually answered straight away. They see the laser light approaching at 1c. And that also answers the third part, and that is that how much faster is the laser light? At what velocity do the aliens see the laser light move away from the cruiser? So it's 1c minus 0.8c, and that comes out to that the laser light is 0.200 times the speed of light faster than what they see the cruiser. Okay, then this part here would have to be calculated with v equals v of the cruiser plus v of the, let's see, this is the ion gun, divide by 1 plus v of the cruiser times v of the ion gun divided by c squared. And then I would have to plug that in and come up with something in terms of the speed of light. And then part D is simply going to be the, let's see, V, the V that I will calculate minus the 0.8c, and that also comes out to some kind of number here in terms of the speed of light. So this particular equation here will tell me how fast the ions approach. Of course, the ions are being fired at 95% the speed of light. The cruiser is already relative to the other one at 80% the speed of light, but these two numbers cannot add. You see, you would come up with 1.75 times the speed of light, and that's impossible. It cannot be faster than the speed of light, so those shall not add the velocities as we're used to, but according to the relativistic velocity addition formula. So I'm going to do that on the calculator. So this one is going to be 0.95 plus 0.8 divided by 1, parentheses, 1 plus 0.95 divided, times 0.8 divided by c squared, which is pretty much, because it's all in terms of c here, 1 squared. Parentheses. Yeah, each one of these numbers is in terms of the speed of light, and I hit the enter button and I come up with 0.994 times the speed of light, and then I would subtract for my answer D down here, I would subtract the speed of the cruiser, which means that this is how much faster the ions seem to approach that second spaceship as the cruiser does in relation. Okay, basically I'm done with the with this problem, but I want to show something else, and that is on the first one. I mean, we figured right away out that that is the speed of light with which the light is approaching. But what if I try to add speed of light to the speed of the cruiser, so 1 plus the 0.8, which I would have to do a relativistic with this formula as well. So let me show you that. I'm actually done with the problem at this point, but let me show you this first part here. So I'm going to do 1 plus 0.8 divided by 1 plus 1 times 0.8 divided by 1 squared, close the parentheses, and I come up with 1. And that means that the light which emerges from this laser gun here, as that speed is being added to the 0.8 here relativistically, still comes out naturally from the equation as 1 times the speed of light. So you can either say that, hey, it's going to be the speed of light anyway, or you could actually add it with the relativistic velocity addition formula, and you come up again with just the speed of light. But as I said, this past minute or so that I recorded was kind of on top of that. I was already done earlier with the problem. This problem reads, two atomic particles approach each other in a head-on collision. Each particle has a mass of 2.16 times 10 to the negative 25 kilograms. The speed of each particle is 2.10 times 10 to the 8th meters per second when measured by an observer standing in the laboratory. What is the speed of one particle as seen by the other particle? Determine the relativistic momentum of one particle as it would be observed by the other. Okay, let's see. Let's write these numbers down here. So each one of these has a mass of 2.16 times 10 to the negative 25 kilograms. And when I compare that to the atomic mass unit, I would divide 216 by 1.6605, and that means I have an isotope with the mass number of 130, and then I compare it to the periodic table, and I'm kind of in the neighborhood of like iodine, xenon, cesium, somewhere around there, these kinds of elements. Not important for the problem, but I figured I might as well point that out. And then it says they have both a speed measured from the laboratory frame of reference of 2.10 times 10 to the 8 meters per second, and if you compare that to the speed of light, that's 0.7 times speed of light, 70% of it, meters per second. Okay, and then of course the other one approaches with the same speed, so maybe I can copy that and put that right there, and I copy this one here and put it right there as well. Okay, as far as the velocity is concerned between these two particles, that's simply the velocity addition formula. So the particle on the left here plus the particle on the right divided by 1 plus these two velocities. Oops, it's supposed to be an r. Divide by c squared. Alright, now technically one of these, presumably this one here, as it's moving to the left, that should be actually a negative. But notice if we plug that in as a negative, then we're simply going to come up with 0. The velocity between the two is 0, and that can't be right. So what's happening here is actually we have to put ourselves into the frame of reference of one of these particles. For example, let's say this one here. And now we have to look at that we see the laboratory itself moving with that speed here. And then the other one is kind of moving towards us as well, on top of what the laboratory is moving towards us, and both of those are moving to the right. So this one is moving to the right, and the laboratory is moving to the right, and we on this particle here consider ourselves at rest in our frame of reference, and therefore we have two positive velocities, and that's why we can consider both of these positive. I know the way I explained it wasn't really the greatest way, but I think I'm just going to leave it at that. In any case, when we plug in these numbers, it's going to come out in meters per second. Moment. So I'll get this one here, and I know it's in meters per second, but I figure I mentioned earlier that this one is actually 0.7 times the speed of light, so let me just plug that in. 0.7 plus 0.7 divide by 1 plus, it's a plus, yeah, 1 plus 0.7 times 0.7 divide by 1 squared. So this is all again in terms of the speed of light, and I hit enter. I think I did correct. So 0.93 times the speed of light, and now I have to get it back into meters per second, and this saved me some work here, just typing it in in terms of speed of light, and then here, what is that? 2.82 times 10 to the 8 meters per second. Okay, then for the momentum, I plug in those numbers, so m times v, where m itself is the rest mass and v is this number here that we just calculated, and then divide by the square root of 1 minus v squared divided by c squared. Take the square root, and then I plug in numbers. So that's going to be, let's see, 2.16 10 to the negative 25 times is 2.82 10 to the 8th meters per second, divide by the square root of 1 minus, see, parentheses, 2.82 8 squared divided by 3.00 E8 10 to the 8th squared. I actually just noticed that sometimes I could have already squared this in my head, which comes out to 9 times 10 to the 16 for the speed of light squared. Let me see, parentheses, and I did everything correct, and I come up with momentum of 1.8 times 10 to the negative 16 kilograms times meters per second for the momentum of one of those particles. And again, I'm not going to write that down, but here's the unit.